Humans possess a built-in mechanism for organizing the chaos of the world. We look at a pile of objects, isolate the differences, and begin sorting them into distinct groups. When we translate that exact cognitive process into machine learning, that pile of objects becomes an instant space. And instead of physical hands, algorithms use mathematical conditions to drop orthogonal lines across that space, slicing the data into increasingly specific, isolated regions. Formally, a decision tree is a non-parametric classifier, meaning it operates without any prior assumptions regarding the distribution or structure of your data. It is expressed as a recursive partition of the instant space. Structurally, it reads like a flowchart. The entire dataset enters through a single root node and hits internal test nodes that dictate how the space is split. Because these tests are isolated to individual nodes, the architecture is uniquely capable of routing an instance even when specific attribute values are missing. But building the optimal version of this structure, finding the absolute minimal tree that flawlessly categorizes a massive dataset, is mathematically NP hard. The sheer volume of possible splits makes calculating the perfect tree impossible for modern computers to process in any practical timeframe. Because calculating a mathematically perfect solution is off the table, data scientists rely on heuristic approximations. This flexible approach allows the trees to ingest raw, varied input features without the extensive manual normalization required by more rigid models. To bypass that computational barrier, modern systems like ID3 and C4.5 employ a top-down framework. These algorithms are structurally greedy. When data reaches an internal node, the system searches exclusively for the single metric that provides the absolute best immediate split for that specific moment. It makes no attempt to calculate the future. The algorithm cannot look ahead to evaluate if taking a slightly less efficient split right now might yield a vastly simpler, more accurate tree 3 layers down. Instead, it relies on a strict divide-and-conquer execution. It subdivides the training set into smaller chunks, applying that exact same localized logic to every new node, over and over until it hits a pre-programmed sapping criterion. This specific approach is highly computationally efficient, but because the logic is short-sighted, the mathematical engine evaluating those splits must be incredibly precise to ensure the resulting tree has real predictive value. Every internal node tests the data with a single objective to maximize the purity of the target variable in the resulting subspaces. Information gain calculates the reduction in entropy. It compares the target's probability vector before the split to the children's weighted impurity after, driving entropy toward zero. Alternatively, the Gini index measures the mathematical divergence between the probability distributions of those new target clusters. But standard information gain has a severe mechanical flaw. It possesses a heavy bias toward input attributes that contain a massive number of distinct values. If you ask the algorithm to sort a population based on social security numbers, every single person gets their own distinct branch. The math records a perfect purity score, but the resulting classifier is completely useless for predicting anything about a new instance. To correct this, researchers deploy the gain ratio. This mathematical fix normalizes the impurity measure, explicitly penalizing splits that rely on overly fragmented domains. The choice of impurity metric, whether it is entropy, Gini, or gain ratio, serves as the fundamental engine dictating exactly how the algorithm chooses to carve up and define the entire instance space. If you let that recursive engine run completely unchecked until every single leaf hits 100% purity, the structure collapses under its own weight. This creates a state called overfitting. The model perfectly memorizes the training data, but in doing so, it captures every random fluctuation, piece of noise, and anomaly present in the sample. The classifier will report near-perfect accuracy during initial lab testing, and then fail completely the moment it processes unseen real-world data.
Data scientists attempt to control this by setting strict stopping criteria, but tightly constrained rules yield underfitted trees that miss the pattern, while loose rules yield overfitted webs that hallucinate patterns. Induction alone cannot produce a robust classifier. To build a model that actually functions, engineers must deliberately trade apparent training accuracy for generalized simplicity. That trade-off is executed through a secondary conceptual phase known as pruning, utilized heavily by algorithms like CART and C4.5 to combat overfitting. In cost complexity pruning, the algorithm traverses the tree bottom up, evaluating every subtree. It calculates if a minuscule error reduction justifies the added structural complexity. If not, that entire cluster is cleanly severed and replaced with a single leaf. C4.5 utilizes error-based pruning. Instead of calculating a size penalty, it uses the upper bound of statistical confidence intervals to estimate the real-world error rate directly from the original training set. These methods have strict validation requirements. Cost complexity requires an entirely separate validation dataset to verify the cuts, while error-based pruning relies purely on a pessimistic statistical correction. By selectively destroying parts of the architecture, pruning ensures the algorithm isolates true underlying correlations rather than blindly memorizing the raw data it was fed. Even equipped with optimal splitting metrics and aggressive pruning, standard univariate decision trees retain a deep architectural weakness. Because a univariate tree splits data based on a single attribute at each node, it struggles to compactly describe concepts where multiple variables must interact simultaneously to produce an outcome. Take a strict Boolean logic function, where y requires either condition A1 and A2 to be true, or condition A3 and A4 to be true. This diagram illustrates what happens when a tree builds that specific logic. To partition mutually exclusive regions, the tree must generate exact duplicate copies of the A1 and A2 subtrees across different branches. The same test logic appears in multiple places simultaneously. In a real-world dataset, this forced duplication dramatically inflates the size of the tree, destroying its primary advantage of human comprehensibility. The strict divide-and-conquer isolation that makes univariate trees so fast to compute also makes them highly inefficient when data features are deeply interdependent. To solve the replication problem, researchers developed a strict architectural intervention designed to force dimensionality reduction, the oblivious decision tree. Look at this diagram. The structure imposes a constraint. Nodes at the same depth level test the same feature. The first level is exclusively attribute A, the next is exclusively attribute H. The ordering remains constant across the entire layer. This rigid, layer-based testing physically prevents the algorithm from spiraling into duplicate subtrees. It naturally acts as a forward feature selection mechanism, forcing the model to evaluate the broader instance space uniformly. By artificially constraining the greedy algorithm's choices at each layer, data scientists actually generate a tighter, more stable, and ultimately more comprehensible classifier. Pushing these classifiers to industrial scale demands even further extensions. Engineers implement fuzzy decision trees to process continuous data shifts, and frameworks like Rainforest to handle datasets that exceed the limits of a server's main memory. The architecture retains its core mechanical flaws. It remains highly sensitive to training noise, and it is permanently bound by the limitations of its greedy, localized heuristics. Yet those flaws are outweighed by the architecture's inherent strengths. Because it makes no assumptions about data distribution, it naturally absorbs missing values and requires almost no manual data preparation before deployment. Deep learning and opaque neural networks dominate modern computation, but decision trees remain the bedrock of classification because they are one of the very few algorithms capable of translating complex probabilistic mathematics into clear sequential logic that a human being can actually read, analyze, and trust.